Record. Now share my screen. All right. So on Monday, we were talking about redox reactions, and we ended on 3A, and I wanted you to attempt 3B on your own and compare to see what I got, right? And so we're looking at combustion reactions here in 3B. So the first thing we start with, and this is what we actually ended on Monday, is just writing out the equation and balancing it. So CO2 gas plus H2O. And the coefficients that we ended on are 2, 9, 6, and 6. Again, to see how I balance that, go back to the end of Monday's lecture video. All right, so now that we have our balance equation, we have to give every element a oxidation number. That's how we can tell what was oxidized and what was reduced. Again, since we're doing redox reactions, we have to remember our acronym of oil rig, where oxidation is loss of electrons, reduction is gain of electrons. And just as a reminder, electrons have a -1 charge. So if you gain electrons, you become more negative. If you lose electrons, you become more positive. All right, so I'm just going to move left to right in determining these redox numbers. So hydrogen is always +1 if it's bound to other elements. So hydrogen is +1, and we have 6 hydrogens. So overall, all of the hydrogens together make a +6. Again, like I said on Monday, though, hydrogen is +1. Don't fall into the mistake of thinking hydrogen is +6. That's when I'm combining all the hydrogens, all right? So we have hydrogen, now we need to do carbon. So C3H6, there's no charge. So all of the redox numbers in C3H6 when added together have to equal 0. That means all of the carbons together, when we add the redox numbers together, have to be -6, because -6 + 6 = 0, which means carbon is -2. The math I was doing there is I have 3 carbons, and I'm asking myself 3 times what equals -6? Well, 3 times -2 equals -6. So my 3 is coming from C3 right there. And so carbon has an oxidation number of -2. Then we go to O2. Any element bound to itself, if you remember our rules, any element that's bound to itself only has a redox number of 0. So oxygen here is 0. Now we move over. CO2. So here we have oxygen in a compound. The majority of time when oxygen is in a compound, it will have a redox number of -2. Again, that's from our rules. We have 2 oxygens. So overall, all of the oxygens are contributing a -4 to the redox numbers. CO2 is a neutral compound because there's no charge. So all of the redox numbers in CO2 when added together have to be 0. We only have 1 carbon, so that math is easy. Carbon has to be 4 because 4 - 4 = 0. So carbon is 4. Then water, oxygen's always -2, hydrogen's always +1. Again, it's a neutral compound. We add all those together, and we see that water is neutral when we look at the oxidation numbers. All right, So that's determining the oxidation numbers. Now we can determine what is oxidized and what is reduced. So oxidation is loss of electrons. That means you become more positive. Carbon went from a -2 to a +4. So carbon became more positive. It lost electrons. So carbon was oxidized. And if you're oxidized, you are called the reducing agent, right? And we talked about that on Monday as well. If you're oxidized, you are the reducing agent. Oxygen went from 0 to -2, and also -2. So oxygen became more negative, which means it gained electrons. So oxygen was reduced, or the oxidizing agent. And in fact, that's why they call it oxidation, because oxygen is usually the oxidizing agent. If oxygen is present, a lot of the times it will be the oxidizing agent. That's why we call it oxidizing, because it involves a lot of oxygen, especially in combustion reactions. So that's the answer to B. Any questions at all about 3B here? If there's no questions, we will move on then. Okay. So that's the end of this PowerPoint. Looks like we do have a question. So what happens if they remain the same? If everything remained the same, like no element changed, then there's no redox reaction. If, for example, in hydrogen, and if it's just one element like hydrogen, then we don't really talk about hydrogen, right? So in our previous example, hydrogen never changed. It was always +1. So it's not oxidized or reduced. It's just not involved in the redox reaction. If no element changes, then that is not a redox reaction. We have no movement of electrons. Right. So let me pull up our new PowerPoint. Okay. And in case you didn't see the news this morning, they just gave out the Nobel Prize for Chemistry. And the Nobel Prize for Chemistry went to Emmanuel Charpentier. I'm probably pronouncing that wrong. And Jennifer Doudna. I'm probably pronouncing that wrong too. Basically, they are the two lead scientists who helped to discover CRISPR. If you've never heard of CRISPR, here's an artist's rendition of what CRISPR looks like on the right. And CRISPR is basically a way to change the genome inside of a cell, right? So usually CRISPR originally is a way for bacteria to fight against viruses, bacteriophages. Humans, scientists, have taken that bacteria defense system and utilized it to change the genome of organisms inside the cell. And so the two scientists there on your left will share a prize of $1.2 million for their work on CRISPR, which is an absolute game changer when it comes to molecular biochemistry. CRISPR has revolutionized how we modify DNA. Could it be used to cut out mutations in genes? So that is one of the big things people want to look at in the future. So cystic fibrosis. Cystic fibrosis is due to a single mutation of a specific protein, one amino acid mutation, where basically it's a water pump that gets mutated to not do its job properly. And so your airways get covered in mucus. It's very hard to breathe. Well, in the future, and this is all theoretical, what if we could just change that mutation using this system to what it is normally? That's like one of the big ideas. Keep in mind, though, using CRISPR on humans is, of course, very ethically murky, right? Because you are changing the DNA of an organism, right? So, and to do a genome change like that, it's much better to do it when it's an embryo than an actual person. It's harder to do on a person. And in fact, there was a scientist in China about 1.5 years ago to 2 years now that actually used this to modify like 2 embryos without telling the rest of the scientific community. So there's 2 twins in China who have had their genome edited using this CRISPR software. I think that scientist is in jail now, in Chinese jail, which is probably not the jail you want to be in. But yeah, so we are there. There's a lot of more research to do before you can do this on humans, but we use this on organisms all the time. Yeah, sorry, this is not physics, so I will not be talking about the physics Nobel Prize, but all the Nobel Prizes are very cool. If you're interested in mutating genomes with CRISPR, after this class, and after you take organic chemistry, see me in 2 years in biochemistry, and we'll talk about CRISPR a little bit, and we'll talk about that scientist. But yeah, that's just your interesting science fact for the day. And if you ever want to win a Nobel Prize, you can get $1.2 million. Not too bad. So CRISPR, along with stem cell research, could potentially eradicate cancer. I mean, theoretically, probably not, though. Because the thing with cancer is just your body like rebelling against yourself, right? So cancer is one of your cells saying, you know what? I don't want to be part of a multicellular organism. I want to take all the food that I can, and I want to mutate, or I want to replicate as much as I want to. And so that's basically what cancer is. It's just one of your cells saying, I'm going to replicate, and you can't stop me. I'm going to take food. You can't stop me. And one of the problems with cancer is that there's so many ways it could happen. So they're using this. Yes, it's a good way to fight against cancer. It's a good way to stop those cancer cells. But the problem with cancer is that it's your own bodies, right? So you can target specific genes in cancer cells that are only found in those cancer cells. That's one of the best ways to fight it. But in my opinion, I don't think, no matter how good we get with biotechnology, I don't think cancer is one of those things that will ever go away permanently. It will be better at fighting it, yes, but I will hesitate to say we will ever eradicate it. That's just my 2 cents. Just because it's so easy for something to go wrong, and it's your own cell. That's why chemotherapy and all those therapies make you super sick, because you're hitting healthy cells as long as getting rid of those cancer cells, because it's your own cell. It's your own body rebelling against yourself. Anyways, again, if you're interested in such topics, please do look at biochemistry. But you have to finish this class in organic chemistry first. So a ways away from that. So what are we talking about? We are not talking about CRISPR today. We are talking about pressure. So pressure, the definition of pressure is force divided by area, right? So that's what pressure is. And our mathematical is just P equals F divided by A. And we use pressure there's a lot of ways pressure is used. So right now, if you have your volume on, you can hear me talk. What is happening is that your computer is spitting out pressure waves or sound waves. this pressure hits your eardrum. And based on the different pressure that hits your eardrum, your body, your nerves are taking that signal, that pressure signal that's hitting your eardrums, and it's going to your brain, and you are taking those pressure sound waves and you're turning that into language, right? So that's basically how talking works, is that your eardrums just get hit by pressure, and depending on the pressure, you know what kind of sound that is. Of course, we can have pain that goes with that. If you're in low pressure, right, your body has pressure on the inside that's constantly pushing out. So if you go into an area of low pressure, the pressure inside your body is greater and your eardrum pushes out. One of the reasons why we need space suits, for many reasons, is that there is like no pressure in space. So one of the ways you can die, many ways, but one of the ways you can die is that your body just, your pressure just kind of pushes out. I mean, you're probably going to freeze to death and suffocate first, but that is another way to do it. When we talk about temperature, these lows and highs on all these squiggly lines, that's just pressure. That's air pressure. And what pressure is on a chemistry term is that you have gas molecules, right? And the force at which these gas molecules hit a surface, that's pressure. And temperature is actually, kind of like a pressure. Well, it's kind of like a speed, right? So, kind of skipping ahead of myself, but we'll talk about it a little bit. For gas molecules, the hotter a gas molecule is, the faster it will move. So higher temp equals higher speed, right? So the faster a gas molecule is, the hotter the gas molecule is, the faster it will travel. And when it hits a surface, the greater the force will be. So when people say it's hot outside, if you want to be super scientific and nerdy about it, what you would say is that gas molecules are moving fast outside and they're hitting my body with a lot of force, taking heat away from me. That's basically what temperature is. When it's cold outside, gas molecules are moving slow. They don't hit my body with that much force. And what happens is that the heat transfers from my body to those gas molecules. So when it's hot, I said it backwards now that I'm thinking about it. When it's hot, those gas molecules hit you so hard, they give you heat. And when it's cold, those gas molecules hit you so slow, they take heat away from you. The slower they move, the more heat they take. Also, the faster they move, the more heat they give you. That's what temperature is, right? And yeah, so that we're going to be talking about pressure today and what it means in terms of chemistry. So popping your ears is like releasing the pressure from your ears. I don't know. That's a good question. And I don't know medically or exactly what's going on, but I know pressure wise, there's just a change in the pressure. So like if you hold your nose and blow out, since your ears are connected to your throat, right? It's all connected, right? You're actually taking pressure from your lungs. And if you close your nose and close your mouth, it has nowhere to go except to your ears. So you're putting more pressure in there and your ears are popping out. Boyles Law. We will talk about Charles Boyles Law today. Okay. Whoa. Bunch of annotations. I've got to undo them. Okay, we're just going to talk about pressure units to begin with, because there are a ton of different pressure units. In chemistry science class, we're usually going to use the atmosphere or the torr. A torr is millimeter of mercury. So I know you can hardly find them now. But when I was in school, we actually still had these around, mercury barometers. And they're basically just like a giant tube and a puddle of mercury. And based on the height of that mercury, you can tell what the pressure is, because the air pressure pushes down on the mercury, which makes the mercury go up in the tube. We call that a torr, or a millimeter of mercury. 1 atmosphere is the pressure at sea level, and we say that's 760 torr, or millimeters of mercury. What you might be more common with, especially if you're a fan of like cars and such, is the idea of PSI, pounds per square inch of pressure. And here, 1 atmosphere is 14.7 PSI. So we're like never going to use PSI in science, but let's just do a low conversion to get us warmed up. So when I go outside on my tires, they say that I should fill them to 35 PSI. How many atmospheres is that? How many torrs is that? So that's where we're going to get started, just a little conversion practice. Do we have to memorize all the units listed in the book for pressure, like the mercury, etc.? Not memorize. I will probably give you like this. If I'm going to give you a conversion between different units of pressure, I would give you that table. So you don't have to memorize like the different conversions. So yeah. Any conversion for pressure, I will give you like 1 atmosphere is 14.7 PSI. One atmosphere is 760 torr. I'll give you that. Okay, so we've done plenty of conversions in this class. Hopefully we're quite comfortable with them now. If I have 35 PSI, there's 14.7 PSI in 1 atmosphere. Unit of PSI cancel out. I'm left with a unit of atmosphere, which is 2.38 atmosphere. But let's look at our sig figs. 35 has 2 sig figs. So our answer should have 2 sig figs, so 2.4 atmospheres. Then to go into torr, I'm actually going to start with 238 again. Even though I rounded up my answer here, when you do math, you don't want to preemptively round. You only want to round when you get to your answer. Otherwise, you're going to get what's called a rounding error. So we start with 2.38 atmospheres. 1 atmosphere, 760 torr. Atmospheres cancel out. We're left with torr, which is 1809. That's a 9.5 torr. Sig figs, again, 2.4. So originally, and 35 as well, originally my starting point was 2 sig figs. So my answer should be 2 sig figs. So I need to use scientific notation. So I move my decimal over once, twice, 3 times. So 1.8 times 10 to the 3 torr is the answer I would be looking for. Any questions? So I got 1.8 times 10 to the 3. You do round. So I rounded my 1,809 to 1.8. You just don't round when you begin to do the math, right? So I would not use 2.4 here because your answer will be slightly different. That's called a rounding error. So you only round at the final answer. To be more precise, I should probably use 2.380, whatever it is, 09, because I already rounded right here, which is actually an error. But basically, only round when you're reporting your final answer. If you're doing any calculations, do not round. Yeah. So that's just our introduction to pressure units. Relatively simple. There we go. So next we're going to get into Boyles Law. Boyles Law says if we have a gas and the temperature of that gas doesn't change and the amount of that gas doesn't change, volume and pressure are actually inversely proportional to each other. So what that means is that if I have a gas and I increase the volume, my pressure goes down. If I increase the pressure, my volume goes down, which makes sense, right? Let's say I have a balloon and I can freely expand or collapse that balloon without popping it. So if I take that balloon in my hands and crush it down, I'm putting more pressure on that balloon, the volume will shrink, right? And let's say I have that balloon like all crushed down and it doesn't pop, and I release my hands, there's no longer that external pressure. So what will happen is that the balloon will expand again. So the volume will increase because the pressure has gone down. And for gases that don't change temperature or amount of moles, we can calculate how pressure and volume changes. And so we have this equation. Pressure at state 1 multiplied by volume at state 1 equals pressure at state 2 multiplied by volume of state 2. All right, so that's Boyles Law. Volume and pressure are inversely proportional to each other. So here's just 2 example problems with Boyles Law, and I even have the equation up there for you. So question 1, I have gas initially at 5.6 liters. The pressure is 735 torr. I want to tell you, or I want you to tell me rather, if we increase that volume of the gas 9.4 liter to 9.4 liters without changing temperature or without changing the amount of stuff, what's our new pressure? And then 2, same idea. We have gas, volume of 13.9 liters, pressure of 1.22 atmospheres. If I compress it to 10.3 liters, what's my new pressure? So everybody take a couple of minutes and get yourself familiar with Boyles Law. Whoops, my bad. Boyles Law and how to use Boyles Law in calculations. So we have a question about Boyle's law and Charles' law. So is Boyle's law the opposite of Charles' law? No, they are looking at different things. So for each one of these laws, right, we are holding something constant. So Boyle's law, what we're looking at is we're looking at how pressure and volume changes if temperature and amount of stuff stays the same. In Charles' law, let me just go ahead 1 second here. In Charles' law, we're saying how do volume and temperature change if pressure and the amount of moles stays the same? So Charles looks at volume and temperature relations. Boyles look at pressure volume relations. So they're looking at two different ideas. Six. All right, so let's take a look at number 1. Again, with these word problems, keep switching, sorry. With these word problems, what you want to do first is just figure out what your variables are. And this is really useful for any type of problem you're doing in any class that has like words and numbers. Just figure out what is going on here. All right. So I have a sample of gas. Initial volume is 5.6 liters. So I'm going to say that's V1 or yeah, V1. And it doesn't matter if you call it V2. All that matters is that V1 is talking about the same gas. So V1, my pressure is 5.6 liters. And at that volume, it says my gas has a pressure of 735 torr. So pressure of sample 1 is 735 torr. Remember, a torr in millimeter of mercury is the same thing. So if the volume of this gas is increased to 9.4, so if I take this gas and increase it to 9.4 liters, what is my pressure? So that's a simple calculation. P1 V1 equals P2 V2. 5.6 times 735 equals 9.4 multiplied by pressure 2. Divide each side by 9.4. You should have 2 sig figs. So it's 4.4 times 10 to the second torr. I think when you actually do the whole calculation, you should get, 437. So when I did this calculation, I got 437 torr. 2 sig figs. So I round up. So it's 3.7, that rounds up to a 4, so 4.4. Same thing for 2. Let's look at 2. We have a gas with an initial volume of 13.9 liters. So V1 equals 13.9 liters. And we say the pressure of this gas, so P1, equals 1.22 atmospheres. If I take this gas and I compress it to a volume of 10.3, so I take this gas and now it's at 10.3 liters, what's my pressure? So again, P1 V1 equals P2 V2, 1.22 times 13.9 equals 10.3 multiplied by pressure 2. Divide each side by 10.3. And I got 1.646 atmospheres, which is, we should have 3 sig figs here, 1.65 atmospheres. Do we have to say torr, or can we say millimeters of mercury? You can say millimeters of mercury. It's just longer to say, has more syllables. Torr has 1 syllable. So that's why I say torr. Takes less time, takes less energy. But torr and millimeter of mercury is the same thing. So either one's fine. Any questions about Boyle's law? More or less straightforward. And just as a reminder, next week is a test. So this PowerPoint, even if we don't finish it today, this PowerPoint will be the last material on the test. And I will give you an equation sheet with like Boyle's law and Charles' law on it. I just won't tell you it's Boyle's law. On the equation sheet, it'll just say P1V1 equals P2V2. All right. So moving on then. And all these laws are like relatively simple. There's nothing tricky going on here. So next we have Charles' law. Charles' law is we have a gas. Pressure doesn't change. The amount of molecules don't change. And what we find is that the volume and temperature are directly proportional. So again, going back to like my balloon example, my example of a balloon that can expand and collapse while breaking. If you take a balloon, and you might have done this when you were a kid, you take a balloon, you put it in a freezer. What happens? It like shrinks a ton because the temperature is decreasing. The gas is not moving fast anymore. And so the volume goes down. While if you have a gas and you put it and you take that balloon and you put it over a fire, again, assuming you don't pop the balloon, what you will see is that this balloon expands a lot, right? So the hotter something is, the hotter a gas is, the bigger the volume. The colder it is, the lower the volume. When we're comparing a gas at different states, Charles' law equation is volume of gas 1 divided by temperature of gas 1, or state 1 rather, equals volume at state 2 divided by temperature at state 2. So that is old Chucky's law, Charles' law. So again, let's see if we can use it. I have 2 questions that's using Charles' law. So 1, we have a sample of gas in a cylinder, warmed from 22 to 87. What is the volume at this final temperature? This is basically how a combustion engine works, right? We have a cylinder of gas. We use gasoline to create a little mini explosion that will give heat to our cylinder, make the gas expand, move a piston. B, we have syringe here. So I have a syringe with 1.55 milliliters of oxygen, and I cool it down to 0. What's the final volume of my gas? So give everybody a couple minutes to work on Charles's law. Ah, yes. So good questions here. Do you need to convert Celsius into Kelvin? You do. I'm glad somebody figured that out, because in B, right? In B, if we do not convert from Celsius to Kelvin, we are dividing by 0. You cannot divide by 0. I cannot put like 8 bananas into 0 boxes. That sentence does not make sense, right? It's not possible, because how can I put something into something that doesn't exist? So to convert from Celsius to Kelvin, you do, let me get my pen out. Celsius, your temperature in Celsius plus 273 equals your temperature in Kelvin. And since I just talked about 0 is one of those concepts that took like people a long time to figure out, because the concept of nothing is really hard to think about. Like, how can you have nothing? Why would something even exist as nothing? Just like the concept of negative numbers, you actually can't have negative things. Like, how can I have a negative pen? Even though the bank says I can have negative money, that's not quite the same thing. You do not need to convert liters. You can keep it as milliliters. That's totally fine. So A, the first thing I need to do is convert my temperature. So I have 22 Kelvin, or Celsius, sorry, plus 273 I keep saying Kelvin preemptively, plus 273 equals 295 Kelvin. So that's temperature 1. And at that temperature, my volume 1 is 48.3 milliliters. All right. So at temperature 2, I heat it up to 87 plus 273, which is 360 Kelvin. What's my new volume? All right. So we just set up this equation where we have, let me make sure I'm looking at the right one. So 48.3 divided by 295 equals my second volume divided by 360. So do the fraction on the left, multiply each side by 360. My volume at this new hotter temperature is 58.94 milliliters. It should be 3 sig figs. So that's 58.9 milliliters. So we got hotter, so our volume should increase. So B, let's take a look at, I don't know why I rewrote B. Let's look at B. So a syringe containing 1.55 milliliters. So that's volume 1. Is cooled from, so thank you, Mail, for making that sound. Okay, there we go. Mail is closed. So it's cooled from 95.3. So that's my initial temperature. So 95.3 plus 273, that is 368. So what's my new volume at my temperature of 0? So 0 plus 273 equals 273. So again, set that up, 1.55. So volume divided by temperature equals volume divided by temperature. V2 is 1.15 mils. Yep. So we got colder, so our volume shrinks. Any questions about Charles's law? Now we have one more law to get to. So all of the temperatures must be converted to Kelvin. Yes, you have to use Kelvin, because as we saw, if you go to 0 Celsius or negative Celsius, these calculations don't make sense. So like you can't have a negative volume. You can't have a volume of 0, right? Even in a vacuum, volume's not 0. There's always something there. And volume, you don't have to be liters. You can be anything, right? This thing works for any metric system. You have to be in the metric system, but you can be in milliliters, you can be in microliters, you can be megaliters, because technically they're all liters, right? If I say milliliters, that is just, all I'm saying is this is 1/1000th of a liter, right? It's still a liter. It's still the unit of a liter. I'm just saying this is 1/1000th of a liter. If I say kiloliter, which is an odd unit, I'm just saying this is 1,000 times a normal liter, but it's still a liter. So as long as you're in the metric system, you don't have to convert out of milli, unless, this is the one caveat, if I gave you volume 1 equals 1.55 milliliters, and I said volume 2 is like 0.0200 liters, both of the liters in your calculation have to be the same volume. You can't do a milliliters and a liters. They either have to be both milliliters or both liters. If you wanted to get out of milliliters into liters, that's fine. You'll get the same answer. Okay. Our last law. Everybody should be familiar with this person's name, because when I ask you a question and you don't know, one of the things I always get thrown back at my face is 6.022 times 10 to the 23. That's Avogadro's number. Well, Avogadro just didn't make that. He also has Avogadros Law. And this is probably the simplest law. But I guess like 200 years ago, this was like novel. Like people didn't know this. So if I have a gas, I don't change the temperature and the pressure. The amount of gas I have is directly proportional to the amount of stuff. Well, no duh. If I take a balloon and I put more gas in it, the balloon gets bigger. If I have a balloon, I take gas out of it, the balloon shrinks. So that is Avogadros Law. He gets his name on that for saying that. Again, 200, 300 years ago, that probably blew people's minds. Nowadays, it's like, yeah, of course, if I put more gas in a balloon, it gets bigger. The actual equation for that is volume divided by the amount of moles equals volume divided by the amount of moles for state 1 and state 2. So our last problem here is just good old Avogadros Law. So I have a balloon that has 0.158 moles of gas. Volume's 2.46. If I add moles to that balloon, what's the new volume? Same thing for B. I have a piston with 0.553 moles of gas. Volume 253. If I add moles to that, what's my new volume? So we are out of time, but I will stick around a couple minutes just to solve this. So I want to, those of you who can stay, see if you can at least get A, set that up, and then I'll go through it here. Those of you who have to go, just make sure you watch the last couple minutes of the video I put up on YouTube. I did not get any of those answers people have privately told me on A. So let's do A here. 1.76. Okay. I know what you did wrong. So again, when you're, this is a good teaching lesson. Avogadros Law says, when I add more moles, my volume should increase. Initially, my volume was 2.46. So those of you who are saying that the new volume is 1.76, after I added 0.113 moles, you just broke Avogadros Law. So this is actually a very, very good lesson and something that all students and all people need to train themselves in. When you get an answer, look at the number and ask yourself, does that make sense, right? So initially, our volume is 2.46. I add more gas. My answer should be bigger than 2.46. That's Avogadros Law. If you calculate a number that's less than 2.46, that means you did something incorrect. So that's a good, what my former boss in grad school used to call a sanity check. Does this make sense just logically? So here, I'll show you what you probably did wrong. So I have a balloon that contains 1.158 moles of gas, so that's N1. Volume of 2.46, V1. So I add an additional 0.113. So what's my new amount of moles? It's my original 0.158 plus 0.113. Those of you who got 1.76, I'm guessing you said N2 is 0.113. You missed an additional, so I'm adding more. And my V2 is, I don't know. So 2.46, so V1 divided by N1 equals my new volume divided by the amount of moles I have, which is 0.271. So I added more stuff, so my volume should increase. And so the volume I get is 4.22 liters. Oops. I'll do B super quick as well. So cylinder with a movable piston has 0.553 moles. So that's my initial starting amount of moles. The volume is 253 milliliters. What is the volume? So V2, what is the volume? I don't know. If I add an additional 0.365. So I originally had 0.553. I'm adding 0.365, right? So my new amount of moles is 0.918. So V1, 253, divided by N1, 0.553, equals V2, I don't know, divided by 0.918. V2 equals 420 milliliters. All right. Any questions about that? Good old Avogadros Law. That is the goal of college. Well, that's the goal of life, actually. You should be learning something new every day if you can. Your brain's a muscle. If you don't keep learning, it'll do what like your other muscles do if you don't keep like exercising them, and it'll just go to flab and you won't be able to think. So make sure you are training your brain every day. All right. Well, that's it for me then. Please don't break Avogadros Law. You might destroy the universe. Other than that, I will see everybody on Friday. Have a good day once I get rid of this. All right. Take care, everybody.